So you're radioactively unstable. What are you going to do about it? There are several ways that decay can occur. There's what's called alpha decay. So I've given you a nice picture of this where you're seeing a polonium atom that's unstable giving away an alpha particle and turning into lead, which is more stable. Alpha decay occurs when an isotope loses 2 protons and 2 neutrons. Beta decay occurs when you have an unstable isotope having a neutron turn into a proton. So what's very interesting about this, if you look at the example of carbon turning into nitrogen, carbon has 6 protons and nitrogen has 7. So you can see if you're looking at the numbers right down here, one of those 6 protons actually turns into a neutron. And there's some other stuff given off with this as well. What's represented by an electron right here is really the same thing as a beta particle. Finally, you can also have what's called positron decay. Positron decay has a proton turning into a neutron. So it's kind of like the opposite of this. So in this case, if you look at, you have 6 protons, 4 neutrons here. This is going to even out to a 5-and-5 ratio by one of your protons turning into a neutron. Gamma decay is very, very common and often accompanies a lot of the other types of radioactive decay. What actually happens in gamma radiation is you have a really high energy unstable nuclei that gives off really high energy electromagnetic radiation or photons. These are not actually particles, they're just energy. So the first 3 that we talked about were particles. This is just energy, and it often accompanies some of the other types of decay. How you're going to decay depends on your proton to neutron ratio. We talked about this band of stability. The nice black line in the middle, if you're looking kind of right there, that represents stable isotopes. So that proton to neutron ratio of stable isotopes. When you talk about alpha radiation, you're going to notice, if you look at this color here, alpha radiation is happening way up here where you have these much larger isotopes. They're kind of trying to get down to that band of stability. You're going to notice there's no more, after right here, there's no more black. So it's very hard to be stable the bigger you get because you have a lot of protons that you're jamming into a small space. So in alpha decay, what you're trying to do is improve your proton to neutron ratio, get it a little bit more stable by giving away 2 protons and 2 neutrons. It helps atoms get smaller, which makes it a little easier for them to be more stable. If you are talking about beta decay, so this blue zone that's above the band of stability, you want to have you have a little bit too many neutrons per proton. So turning a neutron into a proton is a great way to get that ratio a little bit closer to the band of stability. So by turning a neutron to a proton, you kind of improve that stable ratio. And if you have too few neutrons, and it might help you to have some more, then you might turn a proton into a neutron. Now, you don't have to actually worry so much about this or be able to figure this out. You can always look up your decay modes, but I just think it's kind of nice to have an idea of, in nature, why this occurs the way that it does. There are several types of radiation. Please take time right now to open up your reference table. Pause the video if you need to get it out. And you're going to flip in your reference table to reference table N and O. Those are the 2 that we're going to use. So we're going to start with reference table O. Oh, and I'm sorry, there's one thing. It says alpha, beta, and positron decay actually affect the identity of the element. It affects your atomic number and therefore gives you a different identity. Oops, I think that was on the page before. That's okay. Sorry. Video awkwardness. We're continuing. Alpha radiation is when an alpha particle is emitted. That's super important. Particles do have mass. So we're going to look at reference table O, and you'll see your symbol for an alpha particle. The generic symbol looks like this. We can write it with our mass number and our number of protons. This is also represented as He because an alpha particle is the same thing as a helium nucleus. It does not have any electrons, but it does have 2 protons and 2 neutrons. An example of alpha decay that's really common, uranium-238, occurs in nature. When it gives away an alpha particle, it becomes uranium-234. So beta radiation is another type of radiation that we talked about. This is when beta particles are emitted. You'll notice this is a B minus. Top number here is 0. It's a little bit misleading, but we also can represent this as an E because a beta particle is really the same thing as an electron. So when we talk about electrons' mass, remember electrons have what we call a negligible mass. They do have a mass, it's just super, super, super small. So this doesn't actually affect the overall mass of the nucleus because that mass is so small and negligible, but this is a particle and does have mass. So what we actually have occurring here is we have a neutron turning into a proton, and a neutron, remember, is neutral, so it's kind of giving away that negative charge, and it's going to leave us with that positively charged species. Very common example of this is the decay of carbon-14, which allows for radiocarbon dating. Notice what's happening here. You have an increase in atomic number. Your mass is remaining the same, and I'm putting this in quotes because there is a tiny bit of mass lost. It's just so small and fractional, it does not show up in our balanced decay equation. Positron emission, a positron is a B+. This is very, very similar in concept to a beta particle. It's kind of like a positively charged electron. What this really is it's just a little chunk of positive charge that has almost no mass to it. So the charge of a positron is positive. It has negligible mass forming from when a proton changes into a neutron. And a really common example of this is boron transmutating into beryllium. And what you're going to notice here is your atomic number goes down, but your mass number here, again, remember, is going to remain pretty much the same. Not really, but it's negligibly less. When we release gamma radiation, this is very important. This is a ray, not a particle. This is not matter. It's just energy. We don't really write a lot of decay equations with these. You can show a gamma particle or a gamma ray, either of these ways. A gamma ray is just really, really high energy radiation. We could also call these photons. Very frequently, gamma radiation is being emitted along with other types of decay particles. These truly have no mass and truly have no charge. Different types of radiation are going to do some different things. Alpha particles have the weakest penetrating power. They can be blocked by a piece of paper. So all you need is your ref tape and you can block alpha particles from hitting you. Beta radiation have medium penetrating power. They'll go through a piece of paper, but they can easily be blocked by aluminum foil. So if you're worried about those, just make yourself a suit out of aluminum foil. Gamma rays are super strong. They're super powerful. They have super high penetrating power. They're going to go right through paper. They're going to go right through your skin. These are actually involved in the imaging and x-rays and things like that. There's gamma radiation involved in a lot of medical imaging because it goes through soft tissue. Gamma rays are shielded or stopped by concrete or lead. So the reason that you would wear a lead vest when you get an x-ray is to stop that radiation. Also, this is why they build things like nuclear power plants the way that they do. You also need to be aware of how these different types of radiation will act in charged fields. So if we had a positively charged plate up here and a negatively charged plate down here, and all of these types of radiation would be spitting out, the beta particle is being pulled toward the positive plate because it has a charge of -1. Gamma has no charge. You have to actually be matter in order to have charge, and gamma rays are not matter. Alpha particles have a charge of +2, and positrons have a charge of +1, so they're being pulled toward that negative plate. I'm going to pause the video here for a minute and just fill in this chart. It's a summary chart of all the things that we just discussed. So these are 3 of our major types. You'll notice positrons aren't on here. We do talk a little bit less about positrons in some ways, although you will need to write decay equations with them. So take a look at these. It's kind of everything that we just went to. You can go ahead and fill in this chart. It'll be a nice little summary for you to look up each of these types of radiation. Scroll this down again in a moment. You can pause the video if you need to. Okay, for the next part, you are going to need your reference tables. You're going to need N and O. This is the problem-solving part of what we're going to be doing in class. This is important. These are very frequently Regents questions. So we're going to write nuclear decay equations. So you're going to start by finding the starting isotope that's typically given to you, and you need to indicate both protons and mass. Then we're going to find the decay mode on reference table N. So that's will give off an alpha, beta, whatever. Then we're going to write the starting isotope on the left side of the arrow, the decay particle on the right side of the arrow. Then we're going to determine what we're missing by balancing for the mass number, so that top number, and the atomic number. And finally, that'll allow us to fill in the decay product. We will need to go to the periodic table for that as well. It is very important that as you do this, you watch out for paper cuts. You're going to be flipping a lot of pages, so just be really cautious. So we're going to start with francium-220. So you start by writing down your starting isotope. And this is a great time to look and see how many protons it has. So we go to the periodic table, find FR, and you're going to see 87. You're going to determine the decay mode, which is an alpha particle. And you're finding your decay mode, remember, on reference table N. So you find francium-220, and it shows you that. We're going to start with our reactant starting isotope. We have our arrow. We're giving away the decay particle. You can show this as a helium if you're not comfortable writing your little Greek letter. It doesn't matter what you do. Now for our resulting isotope, remember this is functioning like algebra. Everything has to balance. Francium used to have a mass of 220. It lost 4. Now it has a mass of 216. Francium used to have 87 protons. It lost 2. Now it has 85. We then go back to our periodic table. We look up element 85, and it's astatine. We got to check ourselves before we wreck ourselves. So we should have on top 220 equals 4 plus 216. Those should balance out. They do. On the bottom, 87 equals 2 plus 85. They do. Not balancing your equations is bad for your health. Next, we're going to look at gold 198. You then go to the periodic table to find out this is element 79. We're going to determine our decay mode by looking at table N, and be very cautious that that is a beta particle with a -1 on the bottom. Our starting isotope is on the left-hand side. We are giving away this decay particle. Our resulting isotope. So remember, this decay particle does have some mass associated with it, but it's so negligible that we really still stay at 198 for our mass. Now what actually is happening here is a proton's turning into a neutron. So we're losing a proton here. So we had 79 in our starting isotope. A neutron's turning into a proton. I said that the wrong way around, my bad. So we have a neutron turning into a proton. So our atomic number is actually going to go up. So we're going to do 79 plus 1 to give us 80. Mathematically, here's why. If this were a math problem, you would have to add this 1 over here in order to solve this equation. X would equal 80. Because 80 minus 1, which are the two things that are on that side together, equals 79. So we're just kind of treating it like an algebraic equation. So that negative does throw people off, so just be cautious. Element 80, we go to the periodic table, is mercury. If your gold turns into mercury, that's a bummer, dude. So on the top, we have 198 equals 0 plus 198. Balanced. On the bottom, we have 79 equals -1 plus 80. Balanced. One more reaction to look at. we've got the decay of iron 53. Our decay mode for iron 53 is a positron. So this looks a lot like our beta particle, but it has +1 on the bottom. So we're going to start with Fe. I'm sorry, I forgot to write that number up there. You're going to find 26 on the periodic table. We are giving away, and again, you could write a little e here if you don't want to write the beta particle. It doesn't matter as long as you have 0 on top, +1 on the bottom. 53 minus 0 is 53. Because this is a +1, it's 26 minus 1. So in this case, we have a proton turning into a neutron, so we will have a decrease in our atomic number. So 25 here. And according to the periodic table, that is manganese. So let's check our work. On top, we've got 53 equals 0 plus 53. Bottom, 26 equals 1 plus 25. Both of them, check. Good news. No work to be done for gamma radiation. Because gamma radiation has no mass, no charge, no protons, you're going to notice that, that these balance out. So this is 240 for your mass on top equals 236 plus 4. Those balance out. 90 equals 88 plus 2. Those balance out. Gamma radiation does not affect the identity of your species at the end or the mass or anything like that. And in this case, it's actually just accompanying an alpha particle being emitted.